everybody. How are y'all today? Okay. Um, so we
Mr.
have
Compton, I
our,
have a question.
yes,
Do we have class anytime next week?
yes. We have
Monday and
just Monday. Just Monday. Uh, Wednesday and Friday of next week, our Thanksgiving, or part of our Thanksgiving break. We will be looking at um, matrices, which reminds me I probably need to adjust the calendar a little bit. All right. So we have exam 3, Monday and Friday this week. You have the review. You have quizzes. You have homework. Uh, all of that material to study from. So, what can we do today? What questions need to be addressed, looked at? Topics need to be addressed. How can I help you?
Can we go over number review?
Number what?
3?
3? Problem number 3 from the review. X squared plus 5x is greater than or equal to 14. So what we have is we have a quadratic inequality. We have a quadratic inequality. I know it's quadratic because of the x squared, that's the highest degree. And so just like solving a quadratic equation, the first thing I want to do is set this equal to 0, or set the inequality to be greater than or equal to 0. Then I would solve this. I would solve by factoring. So what are the factors of negative 14 that add up to a positive 5? How about a positive 7 and a negative 2? Now, at this point, I'm going to transition. I'm going to get out of this or equal to thing. I'm going to set each of these equal to 0. So you get that x is equal to negative 7 and x is equal to 2. And then what I'm going to do with that information is I'm going to plot it on a number line. Now, we want to know when this function is greater than or equal to 0. Now, if you graph this, you could look at the graph and go by the graph, but let's just pretend like we don't know what this graph looks like. How do we tell when this function is greater than or equal to 0? When is this function positive? Well, I would pick test values. So something nice to plug in that would be in this interval of our number line would be something like negative 10. So I'm just going to plug in negative 10 into this function. That's going to give me 100 minus 50 minus 14. And look, I don't have to pull up my calculator to tell you that this is going to be positive. It's going to be positive. What's something here oh, that's a positive 2, by the way. Not a negative 2. What's something between here? How about 0? And the nice thing about plugging in 0 is you're going to get the constant, which that is negative. Now, because I know what the graph of a quadratic function looks like, I can probably guess that at 2, it's also going to be positive, but let's just go through and plug things in just to verify. 100 squared is going to be 100, plus 50 minus 14. You know, don't have to do a whole lot of work to tell you that that is also positive. So going back to the question, when is this function greater than or equal to 0? Well, it's greater than 0 here and here. But don't forget the or equal to, so we can include the negative 7 and the positive 2. Now, the number line is a nice visual way to represent this, but I would prefer it, in fact, I'm going to request that to put it in interval notation. The interval notation would be from negative infinity to negative 7 inclusive, unioned, including 2 all the way up to infinity. Does that make sense? Alright. What else can we look at?
Number 8.
Number 8. Okay, so we have a rational function. I'm going to go ahead and consider factoring this. And just for notational purposes, we have P of x over Q of x. Now, I know the first problem states what is the domain, but I like to deal with part B first, the vertical asymptotes, because I know if I know what the vertical asymptotes, I know what the restrictions are on the domain. So to find those vertical asymptotes, you're going to set Q of x equal to 0. So that means we have x plus 1 times an x minus 1 is equal to 0, which means that we get x is equal to negative 1 and x is equal to positive 1. There are our vertical asymptotes. And because I know the vertical asymptotes are when the function is undefined, or another way to think about what it means to be undefined, it means what you can't plug into the domain. That means my domain is everything from negative infinity all the way up to negative 1, but not inclusive. Union with everything from negative 1 to 1, unioned with everything from 1 to infinity. So there's our domain of this function. Next question C is what is the horizontal asymptote? And this all has to do with comparing the degrees of P of x and Q of x. So the degree of P of x is equal to 2. The degree of Q of x is also equal to 2. So since 2 is equal to 2, then y is equal to a over b, where a is the leading coefficient of the numerator, so that's 4, for the leading coefficient of the denominator, that's 1, so that means that y is equal to 4. There is our horizontal asymptote. Alright, the next question is find the x-intercepts, D. So to find the x-intercepts, you set p of x equal to 0. So if I have 4x squared equals 0, that means that x must be equal to 0. X must be equal to 0. Which, for part E, I can tell you right now, since I have an x-intercept at 0, I'm going to have a y-intercept at 0. So I know that this is going to be 0, but just for purposes of showing it, you evaluate the function at 0. That's going to give you 0 over negative 1, which is 0. So that means y equals 0. That is our y-intercept. Really, you should put it as a coordinate point. Just like this. That should be a coordinate point. And then this gets us to part F, where we can sketch the graph. Alright, I know I have vertical asymptotes at negative 1 and 1. So I'll draw those with a dotted line. Since I have a color option, I'm going to do red. Okay, and we have a y vertical asymptote at 4. Now, just because I can do this, you can scale your graph however you want. I'm going to put 4 right here. And there's my horizontal asymptote. And the only other bit of information that I have is that I have an x-intercept and a y-intercept here at the origin. We need to get a sketch of this function. So let's start off with what's to the left of this vertical asymptote. Now, just because we should realize, what are our options here? The graph is going to converge this horizontal asymptote no matter what. Now, is it going to go up or is it going to go down? That's the question. Well, it can't go down, because if it went down, it would cross through the x-axis, meaning that you would have a x-intercept somewhere over here to the left of negative 1. But we know that we don't have any other x-intercepts. So I know the graph has to do this. In fact, here's a quick proof. If you do f at, let's say, negative 10, going back over here to our original function, so negative 10 squared is going to be 100. 100 times 4, that's going to be 400. And then 100 minus 1 is 99. And then 400 over 99, I got my calculator here, 400 divided by 99 is a 4.04. So that just proves to show that the graph is existing above the horizontal asymptote. It's going to get closer to it, and as we go this direction, it has to start going up like that. And we can do the same thing for f at positive 10. In fact, it's going to give you the same thing, 400 over 99, which is still going to be that 4.4. Now, what is the graph doing here in the middle? You know, if you think about your potential options, you could do this, you could do this, you could bounce. Because the x-intercept is at this 4x squared that has a multiplicity of 2, I know that the graph is going to bounce. Because of multiplicity. If y'all remember, multiplicity means it bounces. Now, we can prove that without knowing multiplicity. We can do things like this. What is f at a negative 1/2? So that's going to give you 4 times a 1/2 squared, negative 1/2 squared, over a negative 1/2 minus 1. 1/2 squared is a 1/4, so 4 times a quarter over a quarter minus 1. Well, that's going to be 1 over a quarter minus 1 is a negative 3/4, so that's going to be negative. So at negative 1/2, the graph is negative, so that means it's going to be down below the x-axis. And you know what? Since all we're doing is squaring this, f at negative 1/2 is going to be the same thing as f at positive 1/2. So it's also going to be negative, so it's going to go down. So what is the graph doing? It's bouncing. Alright, so I know I went through that rather quickly, but does that make sense how we got the sketch of this function? Then you can ask those last remaining questions. Part G asks, as x goes to negative 1 from the where? From the right. As x goes to negative 1 from the right, the graph is going down to negative infinity. As x goes to 0, the graph is approaching 0. And as x goes out towards infinity, as my x's go out this way, my graph is getting closer and closer and closer to my horizontal asymptote at 4. Okay, what else can we look at?
Number 25.
25. Natural log of the third root of x over e. That's interesting. Let's do it without a calculator. So, the one thing that, of the many things that you got to memorize and know for this test, one of those is this. For y equal to the log base b of x, this is equivalent to b to the y is equal to x. This would probably be the very first thing that if I have trouble memorizing this, I would write it down at the very top of my test. So what we're going to do is we're going to set this equal to y, and then we're going to rewrite in the exponential form. So I'm going to start off by rewriting that natural log as the log base e. Because that's what the natural log is. And then, using this format up here, my base is e, my exponent is y is equal to the third root of x over e. Okay, so let's see. Oh, I am sorry. I misread this. I apologize. I misread this. I thought this was evaluating the logarithmic expression. I misread this. This is not an evaluating. This is an expanding. I apologize. I misread the instructions. This is an expanding operation. So, I apologize. Did not read the full instruction. Oh, I read part of the instructions, not the full instructions. Let's go backwards. I'm going to keep what I boxed in. So the first thing I would do is I would rewrite that third root as x over e raised to the 1/3, which then I would, by the power rule, bring that 1/3 out in front. Then I would expand this using a quotient rule because there's the division sign. Now, take note that this 1/3 is multiplying all of the natural log of e. So when we expand this, you have to think about it like this: 1/3 times the natural log of x minus the natural log of e. Now, there is that part that says, where possible, evaluate the logarithmic expression without using a calculator. Well, I can evaluate the natural log of e, and that just becomes 1/3 times the natural log of x minus 1. Alright, so where do we leave this at? I would accept this answer. Or you could go ahead and distribute that 1/3. I would also accept that. Which is the better answer? I don't know. That's up for debate. So I apologize, I misread the initial problem, but does that make sense how you would expand that logarithm? Okay, good. What else can we look at?
$32.
32. Alright, let's make sure. Solve. Alright, so I read the instructions. Solve. 32, we want to solve. E to 2x minus e to the x minus 6 is equal to 0. So, This is one of those things that the more you see it, the more you realize what you're doing with. This is can be expressed as a quadratic type equation. Why? Because of the 2x squared. So I make note that for e to the x, then e to the x squared is equal to e to the 2x. So that's how I'm realizing that this is a quadratic type equation, because now I can let u be equal to e to the x, then that makes u squared equal to e to the 2x. So now you have u squared minus u minus 6 is equal to 0. Now we can solve this quadratic equation. Alright, so how do we solve quadratic equations? Well, I like to factor if I can. Factors of -6 that add up to a -1. How about a +2 and a -3? Which then means that u is equal to -2 and u is equal to +3. But we have to, that's great, but we don't care about u. We want to know what x is. So this means that we now have e to the x is equal to -2 and e to the x is equal to a +3. Now, right here, we can throw that answer out. Why? Because e to the x is always going to be a positive answer. It's never ever going to be negative. So we can just throw that answer out right there. So how do we solve this? Well, if we take the natural log on both sides, that's going to allow me to use the power rule to bring that out. Natural log of e is 1, so that means x is equal to the natural log of 3. Now, it says to round to 2 decimal places if necessary, or 3 decimal places. So in my calculator, I'm going to do the natural log of 3. And I get a 1.099. Now, take time with these problems to check your work. Take time with these problems to check your work. So, in my calculator, so there's my trying to find the best way to see y'all see that. There's my natural log of 3, 1.099. I'm going to leave that in my calculator. I'm going to plug it into this expression. So we have e raised to 2x, so that's going to be 2. Recall that answer, so a 2-second answer, close parentheses, minus e, sorry, I'm trying to not have that light shining, man, it's so hard to get that to not shine. Recall my second answer, and then minus 6. Alright, now if we do everything correctly, we should get 0. 0, do y'all see that? That's a 0. 0 right there, which means this is our answer. Alright, does that make sense? Good. What else can we look at?
37.
37. Log base 3 of x minus 1 minus the log base 3 of an x plus 2 is equal to 2. So what I would start off doing is I would consider condensing these two logarithms, and since there's a minus sign right there, we're going to use the quotient rule to condense. So this gives us the log base 3 of x minus 1 over an x plus 2 is equal to 2. Now at this point, we have a logarithmic equation. And so I'm going to go back to this relationship that we perhaps wrote at the top of our paper. How do we relate a logarithm to an exponent? So we can rewrite this as 3 raised to the 2 is equal to x minus 1 over an x plus 2. Which then gives us 9 is equal to an x minus 1 over an x plus 2. So how do we solve that equation? How do we solve this equation? Well, one way to solve this is, before I start solving this, I'm going to make a quick note just to declare that x cannot be equal to 2. Negative 2. Of all the possible answers, x cannot be equal to negative 2 because if you plug in negative 2, you get 0 in your denominator. So how do we solve this? Well, I would multiply both sides by x plus 2. So that's going to give me x plus 2 times 9 is equal to x minus 1. Looks like I need to distribute. Then I have a linear equation. So we'll subtract x, so that's going to give me 8x. We'll add 1. I don't know why, I could have subtracted 18. So that gives us 8x is equal to negative 19. Which then means that x is equal to a negative 19/8. Negative 19/8. So how do we check that in our calculator? How do we check that in our calculator? Well, we can first check it over here. We can check it over here. So clear, negative 19 divided by 8 is a negative 2.37. So let's just see if that works here. So in my calculator, I'm going to do recall that answer minus 1 divided by recall that answer plus 2. Oh, we get 9. That's good. Now, the question is, can we plug it in up here? Because remember, we cannot take a logarithm of a negative number. So what was that again? That negative 19/8, that's approximately a negative 2.375. Oh, look, uh-oh. Negative 2.375. If you plug in negative 2.375, you get a negative 3.375. that's less than 0. You cannot take the logarithm of something that's less than 0. Look at this. Negative 2.375 plus 2, that's still going to be less than 0. So if you plug this into either this or this, you get the log base 3 of a negative number. Yikes. You can't do that. So while this works for this expression, it doesn't work in the initial solution, so that can't be it. So that just basically means that we have no solution. Now, your job is to trust your algebra, is to trust the algebra in this situation. Trust the algebra. Now, for verification, if I go to Desmos, I'm going to type that first part in here. So, functions. Log base 3 of the x plus 1, or excuse me, x minus 1, minus my log base 3 of the x plus 2, now, look where that logarithm exists. Look where that logarithm exists. It exists below the x-axis, so all the output values are negative. It exists below the x-axis, and if you set y equal to 2, because that's what the equation is equal to, you can see that this graph will never, ever, ever come up here and interact with the 2. In fact, you could see that we have a horizontal asymptote at 0. This, looks that way. If I zoom far enough out, and then zoom far enough in, alright, so maybe, nope, the graph is still below 0 right there. This is one of those situations where, while the graph is very, very helpful in visualizing the results, you just got to be able to trust the algebra. That's why there's no solution. Does that make sense? Alright. What else can we look at?
$31.
31.
Yes.
E raised to 12 minus 5x minus 7 is equal to 123. So when I look at this equation, I don't like the fact that that variable is up there in the exponential position. So how do I bring it out of the exponential position? Well, I know that if I have e to the x is equal to a, that if I take the natural log on both sides, that we then bring that exponent out of the exponential position. So that's what we're going to do at some point to get x out of the exponential position. But before I do that, I want to isolate this. So We need to isolate that e to the exponential expression. How do we do that? We add 7 to both sides. Alright, now this is all being raised, e is being raised to this entire power. So when we take the natural log of both sides, we have to bring the entire exponent down as an entire expression that is going to multiply the natural log of e. Now, if this was like the natural log of 4, at this point you would need to distribute that natural log of 4 to both into the parentheses, but it's the natural log of e, and we have to know that the natural log of e is 1. So that just means that we have 12 minus 5x is equal to the natural log of 130. Now the natural log of 130 is just a number. It's just a number that we're expressing as a natural log of 130, and it exists as its own thing. So when I go through and subtract 12 on both sides, in our calculators we will do this, but I can't simplify this by saying, oh, this is equivalent to the natural log of 118. I can't take 130 and subtract 12. I have to leave it like this. And then we can divide everything by negative 5, and that gives me x is equal to the natural log of 130 minus 12 over negative 5. Now, there's just a few things in mathematics, in writing, expressing our answers, that we like to follow, and one of those is we do not leave a negative in our denominator. So if I bring that negative out, then you have the opposite of, in fact, it might even be more convenient to put that in parentheses, the opposite of the natural log of 130 minus 12 all over 5. Which this is also equal to, you ready for this? Distribute the negative into the numerator. We like to put our leading coefficient to be positive. You know what's nice about this answer? There's no confusion. Because if I looked at this numerator, and if I just presented it to your average Joe Schmo, they would say, oh, you gotta take the 130 minus the 12. And that could be confusing, but this is not confusing, because now you can clearly see it's 12 minus whatever this is, all divided by 5. Which is approximately, go to our calculator, let's type this in my numerator. I have 12 minus the natural log of 130, close parentheses around the 130, close the denominator, divided by 5, approximately a 1.426. I'm going to go ahead and box it in because I already know the answer to this because we did it in last class, but if you want to check it, come up here and we can plug this into our original expression. So, I have it stored, this is my answer, so I'm going to do second e to the x, so I have second e to the x raised to the 12, then we have minus 5x, so I'm going to recall my answer, close the parentheses, minus 7, and if we did everything correctly, we should get 123. Boom. 123. So that verifies our work that this is indeed the answer to the problem. Does that make sense? Hey, so you got a calculator that you can use on a test. You know, use it to check your answers. I mean, but remember what I'm looking for. If I say, you know, when I say solve, ultimately this is the answer that I'm looking for. This is the answer. I want to see this boxed in because this is the exact answer. And all this is just an approximate. So yeah, approximate if I say so, but this is not the answer I'm looking for. This is the answer I'm looking for. If you express it like this, make sure that I understand that it's the opposite of.
Your conference is scheduled to end in 2 minutes.
The opposite of all of this, and I would do that by putting parentheses around this expression. Do not leave the negative in your denominator. I could be very well tempted to take points off if you leave negative in the denominator. Alright, I got 2 minutes left. Is there anything else that we can look at in those 2 minutes? Alex is shaking his head no. Can't do anything in 2 minutes. I will do my very, very best to get your quizzes from last week graded, posted, and the key posted at some point tomorrow morning. That way you can see what the quiz looked like and use your quiz and the key to address any further questions. I'm available by email, so we can set up a Zoom meeting if you need to, but if you have any other questions over this review or homework or quizzes, shoot me an email before Wednesday. If you send me an email at 10 o'clock on Tuesday night, I'm going to be going to bed, and I'm not going to get to it before Wednesday. So shoot me one tonight or tomorrow morning, and I'll get back to it. Hey, are y'all taking trig next semester? Yay! I got some trig students. Yay! I like trig.
Your conference is now over. Goodbye.
See y'all later. Email me if you have questions. Bye-bye. Bye-bye. Take care. Bye-bye. Yes, so, That's my life. Kid songs. 5 little monkeys jumping on the bed. One fell off and bumped his head. Mama called the doctor and the doctor said, no more monkeys jumping on the bed.